So SpaceX is doing all kinds of cool things lately, and one of the coolest things they're doing is they're designing this new spacesuit. And you can compare their new spacesuit to the original one that NASA and other space organizations have used. But I thought this presented a really nice, interesting opportunity to sort of talk about radiated energy and sort of how to calculate it. And so let's say we're some engineering firm and we're contracted by SpaceX to figure out how much insulation they need for their new spacesuit. Let's say specifically they would like you to calculate the heat that would be radiated from a human body when shaded from the sun in space for 15 minutes. And then they give you the temperatures needed that we need to know. And let's go ahead and draw this. And this is not to scale, but let's say this is the sun. And let's go ahead and draw a big blue Earth. And again, this is not to scale. And then let's add an astronaut hiding behind the sun, or not hiding behind the Earth, I'm sorry, in the shade, so it's shaded from the sun. And so the question is how much energy is leaving this astronaut's body? And if you think about it, since he's in space, he can't be losing any energy through conduction or convection. He has to be losing his energy through radiation, which is a type of thermal energy, but it means he's emitting light to be losing this heat, this energy. And so to figure out how much energy we're losing through radiation, we're given a formula, but if you look, this formula is for power, P, which is not energy, but we do remember that we can use power to solve for energy by saying power equals energy over time. And knowing that, we can say, therefore, let me go ahead and pick a new color here, we can say that energy, or Q, equals power times time. And if we look back at our question, we already know half of this equation. We already know our time. We know that time is equal to 15 minutes. And of course, we can figure out how many seconds that is by multiplying 15 minutes times 60 seconds per minute. And we get 15 minutes is 900 seconds. And so we know our time already. We just need to find our power, which is what this formula is giving us. And so let's see if we have everything we need to know to solve for this. Let's start from the beginning. The first thing they ask for is this symbol called sigma, or Stephan's constant, which is a constant, which means sigma equals 5.6696. 6696. And then we look, it says times 10 to the negative 8. So a super small number, and then we can even write out the units if we want to. It says watts divided by meters squared times Kelvin to the 4th power. And then, of course, because the units are that, is because we're going to multiply this by area, which will cancel out meters squared. And then we're going to multiply by this temperature to the 4th power, which is Kelvin to the 4th power. And we'll be left with watts, which is what power is. And so that's why the units for Stephan's constant are what they are. But anyway, let's look at the next thing we need. We need area. And so area in this case would be surface area, which they gave us. The surface area of your average human body's skin, which is kind of weird to think about. But the average surface area of skin is 1.9 meters squared. And then the next thing, our formula is E, which it says is emissivity constant, and the skin emissivity is apparently 0.9. And then the last two things we need are the two comparing temperatures. And so let's go ahead and say that the human's temperature is T2, and that is, what, 98.6 degrees Fahrenheit. And then let's say the temperature out in space is temperature 1, and that's, what, negative 148 degrees Fahrenheit. But then if you look, it says that temperature, both of the temperatures, need to be in Kelvin. And so to convert Fahrenheit to Kelvin, we're actually going to do that in 2 steps. Let's convert degrees Fahrenheit to degrees Celsius. And we do it this way because there is a formula in our formula sheet for this. We can say that temperature in Celsius equals temperature in Fahrenheit minus 32 divided by 1.8. And I'm getting this from your formula chart. And some formulas don't say divided by 1.8. Some formulas say multiply this by 5/9. But that's actually just another way to write the same equation, and there's a way to work that out. We won't bore ourselves with that detail. Let's just go ahead and use the formula they give us. But then let's convert degrees Celsius to Kelvin. And of course, that's even simpler. To convert Celsius to Kelvin, we'll say T Kelvin equals T Celsius plus 273.15. And so to convert this, let's go ahead and pull out our handy dandy calculator. So we'll go ahead and type it in. We'll say 98.6 minus 32. And then we'll divide that by, what, 1.8? And what do we get? We get 37 degrees Celsius. And then to convert that to Kelvin, we'll just add 273.15. And what do we get? We get 310.15. And so let's go ahead and write that out. We'll say equals 37 degrees Celsius, and that also equals 310.15 Kelvin. And then we can do the exact same thing in our handy-dandy calculator. So let's say negative 148 minus 32, and then divide that by, again, 1.8. And what do we get? We get negative 100 degrees Celsius, and then we just add 273.15. And we get 173.15 Kelvin. And so real quick, we just write that out. And let me go ahead and get the right color here. But we say this is the same thing as saying negative 100 degrees Celsius, and that's the same thing as saying 173.15 Kelvin. And so that's actually the hardest part in my mind, is just converting the temperatures to Kelvin. But if you look at it, we can solve for P by saying that P is the same thing as saying P net in our equation over here. And I won't take the time to write it out because it's going to be really long, and you'll see that when I type it in my calculator, which we'll go ahead and do right now. So let's go ahead and clear our screen and let's start typing it in. Let's start with sigma, which is, what, 5.6696 times 10, and then they hit the exponent button to the negative 8. Then we can leave our exponent and close our parentheses. So that's the first one. Times our area, which is, what, 1.9. And then again, we can close that parentheses and then open it again. We multiply that by our emissivity constant, which is 0.9 for skin, apparently. Then, of course, we just multiply it by T2 to the fourth power minus T1 to the fourth power. And this part gets kind of confusing. We're taking it to the fourth power, both numbers. So what I mean is we're literally going to type it in 310.15, and then we'll hit our exponent button to the fourth power. Then we'll leave our exponent and hit minus 173.15, and then again hit our exponent button. We're taking it to the fourth power. And we can leave and close our parentheses, and this should give us our final, or not our final answer, but our power. And what do we get? We get 809.94. And so let's go ahead and make that 810. And of course, as we said earlier, meters squared cancels out with area, and then Kelvin cancels out with our temperature to the fourth power. And so we're left with watts. And so 810 watts, and of course we can rewrite this to say 810 joules per second. And then the rest is pretty simple. To solve for Q, we'll just plug in our power, which we just said was 810 joules per second. And we'll multiply that by the original time, which we figured out was 900 seconds. And of course, seconds cancel out. And so to get our final answer, we'll just take that in our calculator. We'll say 810 multiplied by 900 seconds. And we'll get in 15 minutes, this human has radiated out 729,000 joules of energy. So, oops, not 729,000 joules of energy. So hopefully you see this problem wasn't really hard. It just had a few steps that may take a little bit of time to figure out. But that's how you calculate radiated energy.